continue. So we saw a linked list idea, insertion, constant time insertion, deletion, but it's not so simple. For example, if you do not have a tail, head and tail, like you don't have a tail pointer, right? Insertion at the end actually takes linear time, right? Because you have to find where the end is. And it's kind of silly because keeping a track of a tail pointer shouldn't be so expensive, right? So let's finish this, right? Before we move on to more generic implementation, right? It will get a little bit trickier. Okay, so right now it's just it's storing right now, or data structure is storing just simple integer data, right? In each node, right? Well, okay, so tail, right? At the beginning we have to update, just in case the tail is empty, we need to update. Tail is actually the new node, right? Head is always going to be a new node, right? Similarly, now this code is much simpler, right? I can just delete almost everything. So I need, of course, this part here, right? It is at end, right? It's guaranteed null pointer, right? It's the very last one. Now, all of this I can delete, right? Well, head should be, if list is empty, we need to do this, right? I can just do this, right? Okay. If head is null pointer, well, tail is also going to be null pointer, right? Of course, right? Tail is also a new node, right? Okay, and that's done, right? We can just return, right? How did we do it here? Because this was last, right? Yeah, we did it last here, right? But here we have else, right? This actually means we actually have to find it, right? If the list is not empty, this is what we have to do. Much simpler, an O1 operation. So tail is next, right? Tail is pointing to the new node on tail is new node, right? In fact, we could rewrite this, right? This is always going to be the case, right? We could refactor this because this is, you know, a simple optimization. I'll do this here, right? Control D, right? Control D, or actually Control X, I guess, delete, right? All right, and we always set the tail to the new node. Okay, so I would say the question is now, right? Tail is new node, right? So, not that tail is the new node. Okay, I need this. This is yeah, tail. Yep, exactly. All right. Now the question is this we could somehow, I don't like this else here. We always check, so tail next, right? Tail next, because if it's not empty, right? If null pointer, right? If head is null pointer means S is empty, right? Tail next, right, means by definition is empty, right? Yeah, because we don't mess with the head then anymore, right? Is it possible that it's only one item? Now we have to think a little bit. Is there going to be a difference between two if only head and tail are same? Head is, okay, so this case, head, we don't touch head at all. Tail next is new node, right? And tail we update. That's fine, right? Yeah, that's fine, right? And we always going to do this, right? If we only have one item, it's not going to matter. And if it's 0 items, we'll have a setup, right? Right? Okay, and we gain. This will be O1 operation again. O1 operation at the end of the list. Okay, printing. Unfortunately, well, printing a list, right? We start at the beginning and we keep going until we reach a null pointer, right? Deletion. Well, we have to. If you don't know where the data is, right, we have to keep finding, and if we find it, we delete it, right? And find node, again, just find it, right? Could we do this, right? Return, null pointer, right? Now, could we use this find node here? I think we could, right? Yeah. Delete data by data, right? So I'm going to get rid of this because it's the same thing as here, right? Current head, it reaches, find. Well, Yeah, no, but unfortunately that's not enough. You see, the thing is, okay, yeah, I would like to replace this, right? Find node gives you a pointer, right? We are, don't copy code, right? We can use a function. Unfortunately, this returns the current pointer, right? But we also need the previous, right? Because we need, so we don't leave our data dangling, right? To delete it, right? We need also the access to the previous one as well, right? Okay. So where to go next, basically, right? So not so. But the thing is, actually, wait, could we? It returns current next. So while current is not null pointer, when it is, okay, yeah. So if it doesn't find it, could we skip? Okay, I'm still thinking. Okay, could we skip it because we don't have previous? Yeah. Well, not much point. We don't really save anything. Okay, but let's check. So add node beginning. Right. Right. So 111. So this should be done to do O1 operation. It's linear, but this one is now should be done, right? Because we're using a tail pointer. All right. And at beginning, print list at beginning, and add some at beginning, add at the beginning. I'll do like 100 here. O1 operation. On print list. Print list. Okay. Let's compile this whole thing, and if it works. Okay, it works on first try, and yes, 100 is in beginning, right? We put 100 in beginning. So yeah, it works. It looks okay. We don't have we should probably add some more functions here. Member functions such as delete everything, but this is now already pretty decent for a singly linked list. But okay, what's the issue with singly linked list? Okay, it's a good data structure, but the issue is that it's still kind of pain to insert things going backwards, for example, right? We can only go forward, right? Going backwards, we can't really go backwards, right? Because we don't have pointers to our previous, to our parents, basically, right? We only to the next, we don't have previous, right? So a simple improvement is to add a link to a previous. Of course, it's not free because it, of course, going to cost some memory, right? These days, memory is pretty cheap, right? So it's usually, when you look at most multiple programming languages, they include doubly linked list because it costs, for the cost of pointer, for each item, you gain ability to have a doubly linked list. So let's implement that. Let's see. So doubly linked list, first and last, right? So we're going to have references to back and forth, basically, right? And data type, right? This is actually how they would do it, but we will do. So our goal is also to do a generic, meaning abstract data type, meaning it will work for any data type. All right, so added tail to singly linked list, So yes, that's added. So let me make new picture. No, don't save this one. So we're gonna have again our my awesome drawing skills, right? Oh no, I want bigger. This Control Z. This fat lines. So ochre. This is ochre color, right? Right. So right. So what's the idea? Idea is to have a right and go backwards, right? So simply doubly linked list, right? And we have pointers, right? Also, I guess I should call this a different color, right? Pointer head, right? Head, right? Now also tail, right? But of course, we also have, right? These two middle guys have pointers both ways, right? Here, right? previous, right? You know, null pointer, right? And null pointer, right? We could add null pointers here. I'll call them, you know, I don't know, red. Null. Oh, I can't. Null. Right? Null. Right. All right. Awesome. All right. So, and we have some data here, of course. Data, right? Data. Make different color. Come on, I can change. Oh. Oh, yeah. Maybe something like this. Okay. Okay. Now we're cooking. All right. All right. Tricks. Yeah. Yeah. All right. All right. Some data. Obviously, it doesn't have to be the same data. All right. So something like this. So this would be a doubly linked list. I'll save it. Doubly linked list. Right. All right. So something like that. So we can traverse both ways, and assuming, of course, if you have a pointer somewhere in the middle, right, we could also insert there, right. And again, but it doesn't have to be null pointer. It could be some sort of other value, right, something to indicate the null sentinel value, right. Also, I mean, it's possible if you keep track, if you think about it, head and tail, you could include a pointer to also to beginning, right, instead of going to null. Assuming you know it's a head and tail, it doesn't have to be a null pointer because it's less pain, right? You have reference to the previous, to the beginning, right? It's up to you how you implement this, right? But let's take a look how we could do it, right? So, a generic. Let's do a generic one. It's going to be a little bit harder. So, a generic doubly linked list, right? Something like this. All right, so we will implement a generic doubly linked list, right? Something like this. So, right. So let's do this. So include IOStream, of course. Why not? Right? And of course using namespace, right? That's given, right? So now we'll do a node structure. Yeah, template T, type name, right? And structure node, right? So next, previous, again, since I'm lazy, I'll do prev, right? We want to, you know, be as short as possible, but so any data type. So, all right. So we can store any integer, strings, some more complex objects, right? As long as they're same. So as long as they're same type, right? So template, right? Yeah. 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 Right. So this far, so easy. We probably also want to put constructor. Well, let's do it constructor. Let's make a constructor. Right, something like this node. Yeah, this would work. Right, or we could do. We will use the new syntax. Right. Yeah, something like this. Right. Bless you. By the way, data. Right. Could be the data kind of, okay, I guess we'll call it value, right? Let's do value. Control D. Let's see, this is value, right? And value, right? I think it will work like this. Will it work? Yeah. Data, value. I think this is how it will work. Let's see, right? Kind of tricky, right? Because this language, it's a little tricky, right? The new syntax, right? We are passing, we don't know what we know it's data type, right? Whatever, maybe integer, right? And we pass it through to we are initializing all three. Of course, we know that next and previous linked lists will be empty, right? So this is the shortest syntax, shortest constructor. Pretty good, right? Again, you don't really need the constructor, not really, not at the moment, right? Because we will be, of course, allocating memory for it, right? Later on. All right. Okay. Now let's do all the last three methods. Now, doubly linked list class, right? Template, right? Type name again. Of course, it will be different T, right? Because when we create, right, class doubly linked list. Linked list, and we can do, of course, we'll do private and public, right? So private is what? Private is going to be what? Next head, oh sorry, control next head tail, right? We need those, right? Obviously. We also want size. We also want size, right? Integer size, or I would say size T, I'll do size T, right? Again, remember what size T? Who remembers? It's basically, yeah, it's basically unsigned integer. See, type unsigned long size T, right? So you get basically double the size of integer, basically, or double size because you don't need a negative size, right? Typically for length we use size T, unsigned integer type. Okay, just an explanation. Okay, that's our private, so to say, right? Do some public. Let's expose ourselves to the public, right? So let's do what? Okay, why is this? I think I need a semicolon, right? I need probably semicolon. Do I? Yeah, I do. I guess, right? So I need, assuming, well, you can say, okay, we are done. No, we're not done, right? Unfortunately, right? We know actual work. So now, of course, I could do this declared here and then move it somewhere else. Let's do this. So we need a constructor. Let's start with let's start with constructor. All right. Again, a new language. Yeah. So basically, B doubly. Let's use the new syntax. Doubly head, tail, size 0, right? So this is the new syntax, right? Head, tail, null pointer, and size is 0, right? Pretty simple, right? Also, we will want to do a deconstructor. Deconstructor. Also, we will want to use deconstructor, deconstructor. The destructor, remember, it will utilize clear all method. Yeah, so simple, right? Of course, at least the pro issue is we need to clear all, right? Could we start with that one? I guess we could, right? So we have head and tail, and notice again, right? So head and tail, we can start with this clear all method, right? Let's do that. So how would we do this? So let's define clear all. So void clear all, right? It's a void function. And do we need everything? Well, no. Actually, let's do this. Well, actually, no, this is correct. But let's do this. Let's do a pop head. Pop head. Yeah, or pop tail, right? Now let's do that first. Let's do it all in once, because just remember to do fix me, right? Remember to define this, right? Head, of course, right? So and I say method, of course, function member functions, right? So add node, that will call this add. I want insert head and insert tail. That's method insert at tail, right? End of the list, right? Now, so we have a value, right? We pass this, a new constructor, right? Set the pointer of the new node to null pointer, right? We know, yeah, a tail. Set the previous pointer to the current tail. That makes sense, right? We are inserting here, right, new data, right? Again, my colors, my ochre color right here, right? Oh, I don't know how to draw this, right? So I need to move this, right? I need to delete it, and right, I can do, right? Tail moves basically here, right? Green color, right? On, right? and then of course this goes here, right, and I go to here as well, right, and this has to be, I can delete, right, and everything is good. And of course the green will be here, as you can imagine here, right. So of course these are next, right, and previous, right, next and previous, next and previous, next and previous, right. Okay, hopefully you can see this, right. This is the smaller font, right, like 18, next, right, on previous, right, prev, right. I hope you see this again, so this is not a, and so on and so on. Next previous, right. So tail and head, right, and null pointer as well. Okay. So instead of tail, previous, if the list is empty, do we need anything else? Yeah, we need to increase the size. Do we have anything else to worry about? New node, value, next null pointer. Do we need this actually? Or, well, yeah, we need this one, of course, the tail, right? If the list is empty, set the head to the new node. Yes. Well, tail, previous is tail. Of course, we don't know what tail was. If the list is not empty, set the next pointer to the current tail of the new node. Right? We always set the tail to the new node here, right? And increment the size of the list, of course, which makes sense, right? That makes sense. Looks okay. We could probably do some optimizations here, but that's okay. All right, I'll save it. Insert a tail. So we can insert a tail, right? And maybe we could also remove a tail, right? Pop tail. Let's pop tail, right? Let's do pop tail. So typically it's actually this return, right? If the list is empty, return pointer. Otherwise, we get the value, right? So we return the data. We return the actual data, right? It's not required, but this is how Python does it, right? And sometimes it doesn't get the pop. We actually return it. Remove the last. It returns. We also return the data of the node we are removing, right? Just in case you want to save. That's kind of nice little extra, right? So if head is tail, right? Delete tail, head no. Okay, so that's a special case. So the thing is, why this is also difficult, if you had to do this from scratch, you had no assistance, is because you have these extra edge cases when you're deleting head or tail, right? And you have very little data. That's where you can make a mistake, right? So if you have if list has more than one node, tail is going to be the previous, right? Delete the tail next, right? Tail previous, right? And delete the last node, bless you, right? And tail next, right? Because we know, right? We can simply delete, right? We can use now, since our new tail has reference to old or old tail, we can use this, right? That's kind of cool. And of course, then tail next is null pointer, right? Of course, because it previously did not have it. So pretty simple, right? Pretty simple. Now we have pop a tail, head, tail, and now we can write also clear, right? Now we can write clear, right? And we don't need this, right? We can just do this clear all using pop a tail, right? Using pop, right? We don't need all of this stuff, right? Because it's all taken care of, right? So it's even simpler, right? Look at this, how simple. So now if you do all this preparative work, clear all works. So we have clear all, right? We're almost ready to go, actually. We'll be able to, we have like 13 minutes. We should be able to at least get the basic version working, basic generic version also. So what else do you want? We also want, let's do a print all, right? So void print list, right? While out, this is helper, right? And we just basically current head, and just keep going until current is not a null pointer. Okay, we have pop a tail, and insert tail, right? Print list, say size, print size, size, okay. There we have it. All right. Now let's see this in action. Yeah, in action. Okay, cool. I think it is reading my voice. No, I don't know why. So int main, right? Oh yeah, we will store person objects in our list, right? So let's do structure person name end, right? So something simple like that, string age, right? We need to insert string, right? We don't have string, do we? Yeah, we need string, right? String, right? Include string. Now we can use this, right? Right, let's do some person, right? So person list, Alice, Bob, Charlie, right? And print list and remove the last. So only thing is see out current data. Yeah, the question is this part here, right? Is printing this person, does this have see out when you're printing this out? That's the only question, right? We could probably want this to for see out, right? Data, right? It's going to be type person. We want a friend, right? Let's overload. Let's have a friend. Yeah, exactly. Right? Friend or stream or friend or stream, and we can at least get name and age. So it should work now, right? Now we have age on person and age. Okay. All right. So now looks like we are in pretty good shape. Assuming this works, everything works. We have some persons, inserting a tail, person list, right? So with all this work, of course, already done by library, but let's see if there are any mistakes. And that's going to be fun, right? Let's see if this is, we went pretty far. It looks good, but I don't say it's, don't trust me on this one, right? Generic the D list. Generic, I don't know, D list. Okay. All right, null point. Oh yeah, of course I need to. Did it include null pointer? Ah, interesting. To person. Line 63. Let's take a look. What's happening here? Generic. If head equals the turn null pointer, well, T, right? If the list is empty, we want right person null pointer, right? Pop a tail, but we are actually returning pop a tail. Ah, but we want to return a data, right? We return a data, but it's not empty, right? What are we return value, right? That's actually data of the list. That's going to be tricky. Do we might be simpler to just not return void, right? That's why it's usually, what I'll do is I'll probably just do nothing, right? Return. I'll just skip this part here, right? Yeah, so we won't see this pop version. Don't have time to fix it, so I will delete void, right? And of course then I just do nothing. I'll return nothing and you'll like it, right? So nothing. And hopefully, right, to fix it, I'll do fix me. Make it so we can return value. For now I'll just return, right? I don't want to mess up too much, right? So now the signature is okay. Return, delete tail, right? Pop. That's maybe the reason why pop is not returning anything oftentimes. Let's try that. Okay, amazing. It compiled on second try, sorry. On second try, let's run it. Generic D list, and it works. Size 3, Alice, Bob, Charlie. Size 2, Alice, Bob. Very good. Works. Everything works, but then we can just do the things we already did, but just add the pop head and add push head, basically, right? So insert a tail. So let's do also insert head. Similarly, now let's do insert at head. Yeah. So it's going to be same logic, right? Again, careful with the these null point. If list is empty, right? tail is, if tail is null pointer, of course tail needs to be the new node, right? Again, we have to keep track of this, right? Again, new node next is head, right? Because it's a it's a new head. So previously it's null pointer. We know head points to nothing. Of course, to null point. I think it's already. Does this actually have it? When we create this constructor, could check if this is to do check if necessary, right? Again, it's not doesn't really hurt anything, right? But it's correct. But maybe I think we already had null pointer by default. I think. Now, what's left? So size increase makes sense. Head is always a new node. Tail is possibly new, but no. So head previously, right? If the list is not empty, right? Then the old head is going to be pointing to the new head, obviously, right? And new node next is the old head. So we combine. So basically, we do what we did here, except insert here. Now, well, I guess we can add also. Let's add Poppet. Let's add Poppet. Same thing, well, right? I would like to return date, but it's gonna be a pain to return because we have I think we have a pointer conversion, right? What are we trying to return? Right? We are trying to return the actual object address, right? That would be the idea, right? But for now, yeah, we're not gonna return anything. For now, we are returning nothing. Well, let's take a look. Void, so obviously void Poppet head. If the list is empty, return nothing, right? Do nothing. If the list has only one node, okay, so this is a little tricky, right? So these are two cases. If head equals to tail, we delete the head. Head is null pointer, tail is null pointer, right? That makes sense. That's a special case. You have to be careful here, right? Otherwise, what do? Head is the new head is the second item, right? We can safely delete the old one, right? And now, of course, we know that the head previously, right? The new head, right, is pointing at nothing. And then, of course, decrement the size of the list. Now, the question, oh yeah, it's safe because we have early return, right? So size, this works because we had early return. So this works because we have early return. If there's nothing to return, right? Okay, so these are basically sort of symmetrical methods. Head a tail, Poppet head, Poppet tail, right? Just very similar, exactly. That's why it's I think in a way it's easier to work with, right? Because it's all you gain lots of functionality, right? It's convenient, right? What else do we want to do, right? I think the book, right? It has a big list. Back, front, we could search, right? Delete specific node, right? We could do that, right? Which matches some data, but that gets kind of tricky, right? Because we have specific data, right? Search for specific item, right? Could we do? So we have print list. Let's do a find node. Yeah, this linear. So let's see if this works. Node, it's gonna find a pointer, right? That makes sense. That's better. Current head. If find node by value, okay, and data not equals to value. Let's see, this is gonna work because we are storing objects. Let's see, return current. Oh, let's take a look. Right? Are we gonna find it? Right? Because data, right? It's tricky, right? Data. What are we storing? We're storing persons, right? We're going to look for specific person, right? And how are we going to compare? It's a little bit tricky. Let's look for Alice, right? And then we can finish and we can go all eat some lunch. Let's find Alice first. Now, let's find Alice. I don't know if it's going to work. Right. So remember, this is a pointer. So pointers are pretty free to, we're not allocating new memory. We are trying to find a pointer. It's possibly a blank pointer. If not, if printed, right? If, yeah, no data, does this have a output, right? I forgot now. Person has an output, right? Yeah, that should work because this is defined, so it should work, right? Good question. It's going to compile. I'm worried. No. So it did not work on current data not equal to value. So because what's happening, this is now we get into messy stuff, right? So template, this is debugging template errors is hell on earth. Look at all this good stuff, right? This is what that gives you C++ a bad name, right? Look at all these template errors, right? The issue is that we don't have the right correct type. There's a mismatch somewhere, right? Unfortunately, it's extremely hard to see. The compiler message is not very helpful, right? So we made here is find node, right? It doesn't say, right, find node, it's going to return some type, right? It should be person node, it looks good to me, right? Is what's the issue here? Find node, it's a pointer, right? On these are, this is correct, right? Oh, value, but the value maybe is not what's the issue, you see? But the same data type, right? Oh, maybe, you know what I think is, this is not defined basically, right? We need to define this option, right? I think, yeah, that's the issue. We need to define comparison for value. I think so. Persons need this, right? We need to yeah, exactly. Right. So this will be a Boolean. Is that going to be enough? Or do we need also same goes for inequality? Right? Right? They're not equal if either are not equal. Age or name, right? Two Alice's but different age, that's not going to be equal. Okay, this might work. Well, let's hold our breath. I wouldn't hold my breath, but it might. Wow, it worked. Okay. All right. So, well, again, sometimes it's very, very messy, but I think we now will try it. Yeah, we found Alice. So I think we earned some food, right? What are we going to do next on Thursday? Let's double check linked list. We're going to look at stack and queue, which is in a way we sort of like it's easier in some ways, right? Stacks and queue are easier to implement than linked lists. This was a hard one. All right. So thank you everyone, and I'll see you on Thursday.